Hello everyone, this is Mr. Couple. In this video, I'll be going over the solutions to the exam style questions for topic 3, thermal physics. There are 3 questions in this video. Please make sure that you've already solved these questions on your own before you watch this video. Here we go. Question 1. This question is about heat and power. Part A. Define what is meant by specific heat capacity of a substance. Alright, so we know this is just the straight up definition equation, or definition question. So we're just going to say the specific heat capacity of a substance is the amount of energy required per unit mass to change the temperature of the substance by 1 Kelvin. Okay, that's it. That's what's meant by a specific heat capacity of a substance. Part B, consider 2 metals that have different specific heat capacities. The energies required to increase the temperature of 1 mole of aluminum and 1 mole of copper by the same amount are about the same. Yet, the specific heat capacities of the 2 metals are very different. Suggest a reason for this. So if you look up the amount of mass that's inside each of these materials, so it turns out that 1 mole of copper is equal to 64 grams, and 1 mole of aluminum is equal to 27 grams. So even though it seems like it's the same amount of the material, 1 mole of aluminum, 1 mole of copper, whoa, that's not what I was looking for there at all. So even though it seems like it's the same amount of material, you got 1 mole of aluminum and 1 mole of copper, it's not the same amount of material because you really have 64 grams of copper but only 27 grams of aluminum. And if you think about the specific heat equation, or the, the heating equation, Q equals mc delta T, what it's telling us is that the same amount of heat is required for the same temperature change, roughly, for between aluminum and copper. But what we know is that copper has a much greater mass. Well, what's the only way, the only possible explanation for how something with a greater mass could have the same amount of heat needed to change its temperature? Well, that's because of the specific heat capacity of copper must be lower. So to answer this question, we will say that the specific heat capacity of copper is less than the specific heat. I'll just say less than aluminum. That word. Let me try to see if I can move this down because I don't like the placement on it right now. There we go. Okay, the specific heat of copper is less than aluminum. And then we'll say this makes up for its increased mass and causes 1 mole of each substance. It doesn't like mole, so I'll just say mole. There we go. This makes up for its increased mass and causes 1 mole of each substance to require the same amount of energy to increase its temperature. All right, so the main idea of this question is that a mole of copper has more mass, but copper has less specific heat. And so those two effects end up balancing out. So for a mole of aluminum and a mole of copper, it ends up taking the same amount of energy to increase its temperature. So it's not that the specific heats are different, it's that we have different amounts of mass. And so it makes sense to say that they have the same amount of energy to heat up both because they have different masses and different specific heats. Next question. A hair dryer consists of a coil that warms air and a fan that blows the warm air out. The coil generates thermal energy at a rate of 600 watts. Air has density 1.25 kilograms per cubic meter and specific heat capacity 990 joules per kilogram per Kelvin. The dryer takes air from the room at 20 degrees Celsius and delivers it at a temperature of 40 degrees Celsius. So that's a lot of information packed in there. So a lot of times when you have like really complicated situations like this, it's really helpful to draw a picture. So that's what I'm going to do. So here's the coil. That's the heating coil within the blow dryer. And what's going to happen is we're going to blow air past it like this. So that's my air. And what it said was it's taking the air from 20 degrees Celsius and it's delivering at 40 degrees Celsius. So as the air blows past this coil, it's going to absorb some energy from the coil and raise its temperature. So it told us that air has density 1.25 kilograms per cubic meter and has specific heat capacity 990 joules per kilogram per Kelvin. So we need to take this information and calculate something that sounds really strange because it's not a quantity that's in any of our equations. What mass of air goes through, I gotta stop doing that. What mass of air blows through the dryer per second? So we're trying to figure out the mass of air per second. So the equation Q equals mc delta T, Q equals mc delta T, well, it has mass in it, but it doesn't have per second in it. So we have a problem, but that problem can be fixed because we know that Q is also equal to power times time. That power is the energy per second, like a watt is a joule per second. So we can replace the Q with power multiplied by time. And that's great because it gave us the power of the blow dryer, 600 watts of energy transfer rate. And so we just have to replace Q with PT. And if you do that, if you write power times time equals mass times specific heat times the change in temperature. Now we can find m over T because the T is right there. So if we divide both sides by T, then we can actually find m over T, and then the m over T will be right there. So now all I have to do is just solve for what m over T would be. And so what we'd get is delta m over delta T. And now the reason I'm putting deltas here is because generally a rate of change like this that's how you express it. You express it as a change in mass over a change in time. It's the rate of change of mass is how you would say that. So anyway, if I solve for m over T, what we notice happening here is that we need to divide both sides by C delta T. So we'd have P over C delta T. Power divided by the specific heat times the change in temperature. Well, it told us what the power is. In the question, it said the power was 600. The specific heat capacity is 990. And that told us that the change in temperature, well, it went from 20 to 40. So that's a change in temperature of 20 degrees. So let's do this. So the power was 600, 990. And then let's put the units in here. So this is joules per second. This is joules per kilogram per Kelvin. And then the temperature change was 20 Kelvin. Remember, a change of 20 Celsius is the same as a change of 20 Kelvin. It's the same magnitude temperature change. If we look at what happens to the units, so let's see, we got joules are going to cancel out, the kelvins are going to cancel out, and we're going to end up with kilograms per second as the unit. And so you can see that it's per seconds per kilogram, but a per second per kilogram is a kilogram per second. And now I just have to throw this in. That's good because that's what we wanted. We wanted kilograms per second. So this is going to work. So 600 divided by, and then I just have to do 990 times 20. And so we get this incredibly small number. Well, it makes sense. This is a kilogram. This is air. Kilograms are pretty heavy, like 2.2 pounds. And so, yeah, you're not going to be pushing that much air out of a blow dryer. So we end up getting that the equals is 0.30. I messed up. 0.030 kilograms per second. I mean, it might be more efficient to have written that as 3.0 times 10 to the negative 2, but hey, it is what it is. That's how I did it. What volume of air flows per second? We have the mass flow per second, so we just need to turn a mass flow per second into a volume flow per second. The way to do that is by relating the density, which they gave us. They gave us the density right here. We just need to relate the density to that. Density relates mass and volume. So the expression for that is density. That's the Greek letter rho, if you guys aren't familiar with that. Density is mass over volume. We know what the mass flow rate is, and so we just want to find what the volume flow rate is. So you could very clearly see from this equation that the volume flow rate should be the mass flow rate divided by the density. So if we just solve this for the volume, we'll see that the volume is the mass divided by the density. And so if I just divide both sides by delta T, then we end up with m over delta T, the mass flow rate, divided by the density is the volume flow rate. So the volume flow rate, which is delta V over delta T, the rate of change of volume, the flow rate of volume is just going to be the mass flow rate divided by the density. The mass flow rate was 0.030. I'll just put another extra digit on there to avoid any rounding errors because we always want to carry that one extra digit. Divided by the density. So down, I'm looking at this part right there. The density was 1.25. 1.25 kilograms per cubic meter. And now let's just make sure that we get the correct units. So we'd expect to have volume per second or volume per time, which is going to be cubic meters per second. So we notice that the kilograms cancel out, which is good because we wanted the dividing by the density to get rid of the mass, just turn it into a volume. And then we can see that it's per seconds per cubic meter. So that's cubic meter per second. That is indeed a volume flow rate. And so we're going to end up getting, so we're going to take that number and we're going to divide it by 1.25. And we get the answer 0.024. So this time I'm going to learn from mistakes from last time and write this in scientific notation. So 2.4 times 10 to the negative 2 meters cubed per second. So that's the volume of air that the blow dryer is blowing. Part E, the warm air makes water in the hair evaporate. If the mass of water in the hair is 180 grams, calculate how long it will take to dry the hair. The heat required to evaporate 1 gram of water at 40 degrees Celsius is 2,200 joules. Okay, so we're going to try to estimate how long it will take for your hair to dry when you're using a blow dryer. So obviously this depends upon the amount of hair that you have. You know, if you have like really long flowing hair, lots more water can fit in it. It might take upwards of an hour to dry your hair. Whereas if you have very short hair, it could take a couple of minutes. So we're just saying that there's 180 grams of water in the hair. So let's find out how long it will take. Well, anytime that it's talking about how long it will take, we know that we're going to be talking about power in some capacity. It's also saying the heat required. So we definitely know that we have to start this question with the power energy relation. Power is energy over time. We can solve this for time. So the time that it takes for the hair to dry will simply be the amount of energy that we need to dry the hair divided by the rate at which we're transferring energy. So the time is just going to be the energy divided by the power. The energy that we need to transfer to the hair, well, there's two things we have to do to the hair. So first, we have to take the water in the hair that's at room temperature, and we need to heat it up to 20 degrees Celsius. And the second thing we need to do is we need to actually evaporate the water. And it told us right there how much energy it takes to evaporate the water. The first thing we do is heat up the water, so that's MC delta T. And the second thing we do is evaporate the water, which is ML, the latent heat. And then we just need to divide by the power. And all of these quantities are known, and we can just plug them in. So here we go. So the time is going to be equal to, that's 180 grams times the specific heat. Now, because this is in grams, I'm not going to write the specific heat as 990. I'm going to write it as 0.9. And the way I'm doing that is I'm just dividing by 1,000. So that way, instead of being per kilogram, it's per gram. So I'm going to write this as 0.99. It's just a little shortcut. So I don't have to worry about grams and kilograms and all that stuff. I'll just switch that over to being per grams. And then I need to multiply by 20 because that's the temperature change that we're getting for the hair. Add to that the mass of the water, which was 180, times the latent heat that they gave us. It takes 2,200 joules for each kilogram. So that means that, or for each gram, since there's 180 grams and each one's going to take 2,200, we just have to multiply them together. We divide that by the power, which is 600 watts, which is the amount of power that the hair dryer is outputting. Here we go. So 180, come on, 180 times 0.99 times 20. We're taking that plus 180 times 2200, and then that's going to get divided by 600. So that's going to give us a time in, what is that? That's seconds. That's a time in seconds. So we probably don't want that in seconds, but let's just leave it in seconds anyway. So T is going to equal about 600 and let's say 70 seconds. Well, we can turn this into minutes. All we have to do is just divide that by 60. And so what's that? It's about 11 minutes or so. So it's about 11 minutes. And that checks out if you've ever tried to blow dry your hair before. It's usually around that amount of time. It's probably not going to be less than 10 minutes, and it's probably not going to be longer than an hour. So it's somewhere around 11 minutes. It just depends upon how much hair you have, how much water there is in your hair. But that checks out. Question 2. The volume of air in a car tire is about 1.5 times 10 to the negative 2 cubic meters at a temperature of 0 degrees Celsius and pressure 250 kilopascal. Note, in British English, used by the IB organization, tire is how you spell tire. Part A, calculate the number of molecules in the tire. So this is kind of annoying because, we'd have an equation, PV equals nRT. Oh my god, I did it again. We have an equation, PV equals nRT. The problem, though, is that N is not molecules, that's moles. So we have to convert from moles into molecules. Well, the way to do that is we say that the number of molecules is the number of moles times Avogadro's constant. So realize that we can replace the little n with big N, number of molecules, divided by Avogadro's number. But if we do that, you realize that what's happening is you're just changing this equation to the other form of the equation, which is PV equals big N KB times T. And I can show you a little bit more about why that works. The reason is because R divided by Avogadro's number, that's Boltzmann's constant. And so if we divide this top equation by Avogadro's number, then what happens is the N, so that's over here. What am I trying to say? If we divide this by NA, that's what I'm trying to do. Yeah, there we go. So if I do that, then you can see that we can substitute little n for big N over NA. So now this little n is big N over NA. And then we end up with R over NA. And so we can just substitute in Boltzmann's constant. Yeah, it's confusing. They don't really care about you knowing this. If you look in the data booklet, so if we go to the thermal physics section, you can see that they give it to you here. So where is it? Oh, okay, there it is. So they show you, actually no, they don't. They just give you the mole equation. Okay, interesting. But you can see it here that KB is R over NA. And so they show it to you there that KB is R over NA. And so what I'm trying to show you guys is that the ideal gas law can be rewritten as PV equals number of particles times Boltzmann's constant times temperature. So yeah, there it is. Okay, so back over to here. So why am I using this? Well, because it asked for number of molecules. I mean, I guess I could have found the number of moles and then converted it over into molecules as an alternative solution, but I decided to do it this way. Okay, so now I just need to solve for the number of molecules. So the number of molecules is going to be the pressure times the volume divided by Boltzmann's constant times the temperature. And then we just have to plug those numbers in. So I was trying to select. There we go. So now we're just going to plug the numbers in. So the number of molecules is going to be the pressure, which it said was 250. Let me make sure that's right. Yeah, 250 kilopascals. So I have to remember the kilo. And then I'm going to multiply by the volume, which was 1.5 times 10 to the negative 2. We're going to divide by Boltzmann's constant. And Boltzmann's constant, if we don't remember what it is, we can just go look at the IB data booklet. Boltzmann's constant is 1.38 times 10 to the negative 27. The way I always like to remember it is that it's as small as the mole is large. So Boltzmann, I can't even say it, guys. Boltzmann's constant is the same power, just negative. So Boltzmann's constant is as small as Avogadro's number is large. So to recap, that's 1.38 times 10 to the negative 23. So I got the Boltzmann's constant, I just multiply by the temperature. But the temperature is not 0. You don't put it in Celsius, you always plug in Kelvin. So we need to write 273 for this. So now I'm just going to plug all this in the calculator, big mess. So 250 times 10 to the third power times 1.5 times 10 to the negative 2 divided by, open a parentheses, 1.38 times 10 to the negative 23. And that, I'm making sure that I'm dividing by all of this, 273. Okay, and then we hit enter. We get 9.95, 9.95. times 10 to the 23rd. And there are no units on this because it's just a number. There's no unit associated with this number. It's just a number that's been counted. So we could say that this is approximately 1 times 10 to the 24 number of molecules inside the tire, number of molecules of air inside the tire. Explain why after the tire is driven for a while, the pressure of the air in the tire will increase. All right, so when you think about a tire rolling along the ground, what will happen is this part of the tire that's making contact with the ground gets a little bit squished. So I'm going to try to draw like a squish there. And what happens is as the tire rotates, so the tire is going to roll as the car is moving, the tire is going to be rolling, and that squishy part is going to end up staying there. The squish stays on the bottom, but the tire rotates through that squish. So the effect is that when the tire is on the bottom, it gets squished, and when it rotates and rotates up to the top, it gets stretched, and then the tire rotates to the bottom and gets squished, and so it's constantly in the state of being flexed, where it's being expanded and contracted, and expanded and contracted. And so we want our answer to mention that. So here we go. So we'll say that as, see if I can, I probably shouldn't have put that drawing there because now I don't have, let me move it off to the side. Okay, so what we're going to write down is we're going to say that as the tire rolls, did I have enough space there? Nope, let's try that again. Okay, so as the tire rolls, you'll notice that I don't need to use the funky IB spelling. I can spell it like an American. There's nothing wrong with spelling it the way we want to spell it, but they're going to publish the test in their standard version of English, which is the British English. But we can still use our American English if we want to. As the tire rolls along the ground, the rubber lining of the tire expands and contracts, which generates heat. This increases the temperature of the air in the tire, which subsequently increases the pressure of the air in the tire. All right, so we have this relationship between temperature and pressure, and so we know from PV equals nRT, I'll just write it down here, from PV equals, let me zoom out in case you guys are still trying to read that, PV equals nRT. So what we just said was that we're increasing the temperature, and so that has to result in an increase in pressure. Part C, calculate the new pressure of the tire when the temperature increases to 35 Celsius and the volume expands to 1.6 times 10 to the negative 2. So they're also saying that in addition to getting a little bit of increased pressure, we're also getting an increased volume. So the volume is not held constant, and that's perfectly fine. There's nothing wrong with that. But the trick here is to know that PV equals nRT, that quantity has stuff that's going to be constant in it. What's the stuff that's going to be constant? Well, it's a sealed tire, so there's no particles are going to be able to escape, and the gas constant is constant. And so we know that PV divided by T is equal to constant stuff. And so we know that if we change the pressure and the volume and the temperature, that this ratio has to maintain. So P1 times V1 divided by T1 has to be equal to P2 times V2 divided by T2. And what we want to do is solve that for the new pressure. Since the question is asking us to calculate the new pressure, then we need to solve that for P2. Solving that for P2 means multiplying both sides by T2 and dividing both sides by V2. And so we'll end up with P2 is equal to, okay, here we go. So the T2 is going to come up to the top. So I'm going to have T2 over T1 times, and then the V2 is going to go to the bottom. That's V1 over V2 times the original pressure. Now we just have to plug in what all of these quantities are, and we'll be good to go. So the pressure of the new pressure is going to be equal to the original temperature. The new temperature, which is 35. Well, actually, it's 35 plus 273. So let's figure out what that is. 35 plus 273. So the new temperature is 308. The original temperature was 273. That's going to get multiplied by the original volume, volume 1, which was up here, 1.5 times 10 to the negative 2. We'll 1.5 times 10 to the negative 2, divided by the new volume, which is 1.6 times 10 to the negative 2. And then we're just going to multiply by the pressure, the original pressure, which was 250 kilopascals. So let's go check to make sure that I'm remembering that correctly. Yep, 250. I don't mean to cross it out. 250 kilopascals. Okay, just got to throw this in the calculator. One thing to notice is the negative 2's cancel out, so save yourself some time when you go to plug this in. So we're going to have 308 times 1.5 divided by 273 times 1.6. So we're going to have, this is the coefficient, so it's going to be this many times larger than 250. So times 250. So the pressure will increase, was that about 5%? So the pressure will increase by about 5%. So we get that P2 is equal to 260 kilopascals. The car is parked for the night, and the volume, pressure, and temperature of the tire, of the air in the tire, return to their initial values. So we're back up to here again. So we've let the car sit, and we've returned the pressure, and now we're letting the car sit overnight. Well, it turns out that there's a small leak in the tire, and it reduces the pressure from 250,000 pascals down to 230,000 pascals over the course of 8 hours. Estimate stating any assumptions you make. Okay, here we go. So the average rate of loss of molecules. So we want to estimate the average rate that molecules are going to get lost. Okay, so what I'm going to use is that other version of the ideal gas law. PV equals NKB. And the reason I'm using this is because they're talking about molecules. And so I want to make sure that I'm not using the one that talks about moles, but rather using one that talks about molecules. So what are the assumptions we're going to make? We're going to assume that the tire doesn't change in volume. We're going to assume that the temperature stays constant as well. Yeah, there's no change in temperature, and that the temperature stays constant. So those are our assumptions. So we'll state those assumptions to begin with. So we'll say assume constant volume and temperature. Okay, I want to make this a little bit wider. Drop it down. Okay, cool. Assume constant volume and temperature. So if we do that, what we can see over here is that, well, this stuff is constant anyway. This, and then, no. Number of particles isn't constant. The KB is constant. There we go. So what we can see is that P equals N. So what will happen is if we put all the constant stuff on one side and all the not constant stuff on one side, you'll end up getting this expression that says P divided by N equals constant stuff. So I'm just moving the N to the other side, moving the V to the other side. So all the constant stuff on one side, all the not constant stuff on one side. So the ratio of the pressure divided by the number of particles, number of molecules, will have to remain constant. So that means that pressure divided by the number of particles is going to equal to constant. So we can derive this relationship that says P1 over N1 equals to P2 over N2. And so now what we want to do is we want to figure out what N2 is. So from this, we can deduce N2. So let's figure out what N2 is. So N2, the number of particles that are going to be left after the leak, N2 is going to be P1 over P2 times N1. What the heck is N1? Well, we know what N1 is because we found it up here. It's 9.95 times 10 to the 23rd. So basically, we just need to take the ratio of these pressures, and that'll give us the times that ratio of the original particles, and that'll give us the number of particles that are left. So N2 is going to be equal to, here we go. So we're just going to take the first pressure, which is 230, divided by 250, and then that's going to be multiplied by that 9.95 times 10 to the 23rd, the number of particles we started with. And that'll give us how many particles we end with. So here we go, so 230 divided by 250. So that means 92% of the particles remain. I'm going to multiply that by 9.95 times 10 to the 23rd. So this is how many particles are left. So the number of particles that remain are 9.15 times 10 to the 23rd. And then I'm going to put a reminder to myself that this is the amount that remain. Okay, it wants us to find the average rate of loss. Okay, so we know how much we started with, we know how much we ended with, and we know how much time it took. So all we have to do is find out how many molecules left in this time, and then divide by the time. And that'll give us the rate of loss. So the rate of loss is per time. So we're going to take the delta n over delta t, which is what we're looking for. So delta n over delta t. All right, so the rate that we're losing particles, here we go. So it's the amount we started with, 9.95 times 10 to the 23rd, subtracted by the amount that we remained, and that gives us the amount that we lost. And then we're going to divide by the time, which was 8 hours. So I'm just going to multiply that by 60 and then by another 60. And so that way I get it in per second. So we're going to calculate the number of molecules per second that leave the tire. So 9.95 times 10 to the 23rd, subtracted by this number, and then divided by 8 times 3600. And so we end up getting this as the result, which is the rate of loss of molecules is 2.8 times 10 to the 18 per second. There is a per second there because we divided by the seconds. So we took a number that had no unit and we divided by something that had a unit, and so it ends up being a per second. So 2.8 times 10 to the 18 molecules per second, that's a lot, are escaping the tire. Question 2, the total mass of air lost. Take the molar mass of air to be 29 grams per mole. Okay, so now we have to figure out the amount of mass that this has. So we know that air has 29 grams per mole. Well, the question is, how much mole is there? How many moles is there in what we lost? The amount that we lost, the particles that we lost, is this part here. So this is the amount that was lost. So we need to recalculate that. And I think, did I have it in my calculator? I did, 7.96 times 10 to the 22. So what we're going to do is we're going to take that. I guess I should show you guys what I'm going to do more clearly. Okay, so the number of moles is the number of particles divided by Avogadro's number. So I'm going to calculate how many moles this is. So 7.96 times 10 to the 22 molecules divided by 6.02 times 10 to the 23rd per mole, since that's Avogadro's number. This will give us the number of moles. So if we take that 7.96 times 10 to the 22 and I divide by 6.02 times 10 to the 23rd, now I have the number of moles. So it's a very small amount. It's 0.13, and I'll carry an extra digit just to avoid rounding errors. Moles. So we have that many moles. Well, now how do we figure out the mass? Well, the mass is simply a matter of multiplying by the grams per mole. And so we know that it gave it to us. It said it right there. So we know that the mass is going to be that many moles, 0.132 moles, times 29 grams per mole. And then we see that the moles are going to cancel out, and we'll just end up with grams. So just to multiply this by 29, and then I know the amount of mass. So we're looking at 3.8. And now what's the unit? It's not kilograms, because this is grams. So this is 3.8 grams. So in that 8-hour period, 3.8 grams of air escaped out of the tire. Question 3. This question is about internal energy and specific heat capacity. Part A. Describe what is meant by the internal energy of a substance. Okay, so the internal energy of a substance. The internal energy of a substance is the total random kinetic, I'll say molecular kinetic energy, plus the intermolecular potential energy of the molecules in the substance. That's it. I guess I probably gave you too much space there, but maybe, we could have used a little bit more space up here, but alas. Okay, cool. Part B, a student claims that the Kelvin temperature of a body is a measure of its internal energy. Explain why the student is not correct by referencing to a solid melting. Okay, so I'm going to do two statements here. So first, the Kelvin temperature, should that be a capital K? Probably. I'll just leave it as lowercase k. The Kelvin temperature, which means the absolute temperature, is a result of the average kinetic energy of the molecules in the sample. Okay, not the internal energy. So temperature only is captured by the kinetic energy of the particles. It's not captured by the internal energy. The internal energy includes kinetic and potential. So the way to remember it is that internal energy is kinetic energy plus potential energy. The Kelvin temperature is only capturing the kinetic energy. And that's from this equation, that the Kelvin temperature is from the 3/2 kBT. So the Kelvin temperature is only capturing the random, average random kinetic energy of the particles. Okay, so that was my first statement. This is a 2-mark question, so I need one more statement. So my second statement is going to say, melting a solid is an increase in temperature without a change, not increase in temperature. Melting a solid is an increase in internal energy without an increase in temperature. Hence, the student is not correct. So we first of all said the misconception was that the student thought that internal energy is all there is, but actually there's also potential energy. It's just usually what happens is when you're dealing with an ideal gas, the internal energy ends up being entirely kinetic because an ideal gas has no, by definition, another gas has no interparticle potential energy. And so that's the confusion that the student is having, is they're confusing an ideal gas for all bodies. This is true for an ideal gas. The Kelvin temperature of an ideal gas is a measure of its internal energy, but that is not true for any body. In an experiment, a heater of power 35 watts, so that's important, heater power 35 watts is used to warm 0.240 kilograms of a liquid in an uninsulated container. So this is the most important part of this question, uninsulated container. This is the problem with, one of the problems that students have with physics is like, a seemingly innocuous statement ends up being the most important thing in this whole problem. The graph shows the variation with time of the temperature of the liquid. All right, so what we notice is in the beginning phases, its temperature is changing quite rapidly. The delta T over T is fast, and then it starts to slow, and then to the point where it's starting to almost go to zero change. This substance is approaching constant temperature. So why is it? Well, one reason a substance can approach constant temperature is because it's going to start to boil. So as soon as an object reaches its boiling point, all the energy that you add goes into separating the particles from each other to increasing the potential energy, the intermolecular potential energy, rather than increasing the temperature. But it very clearly says here that the liquid never reaches its boiling point. So what the heck is going on? Question mark. Well, it's because the container was uninsulated. So if you think about drawing a picture of this situation, so here's the container, whoops. So here's the container, and then here's our liquid in the container. And what's happening is, as we're heating this thing, as we're adding heat to it, there's also heat that's coming off of it. So actually what we should say is the power in. So the power into this thing, from the heater, maybe there's like flames down here that are heating this. Those don't look like flames. I'm not an artist, guys. So let's try and make some good looking flames here. All right, so I give up. So we got flames here. And so the power in, which is how much? 35 watts. If the temperature is constant, then that means the amount of power that the substance is absorbing is equal to the amount of power that the substance is releasing. And so we know that when the temperature is constant, that the power in is equal to the power out. It's like suggests why the temperature liquid approaches a constant value, and so that's what we just said. Is we said that the so let's write this out. So we'll say that the container, let's just say it like this. Since the container is not insulated, the liquid is radiating energy into the surroundings. The liquid will reach a constant temperature when the power radiated is equal to the power supplied. Something like that. And your terminology can be different there. I decided to talk about power because it talks about power up here in the question, but maybe you don't need to talk about power down there. You can talk about like energy, talk about heat. You can say like the amount of heat gained is equal to the heat loss, but really this is a time. This is over time. And so we should absolutely be talking about power when we talk about this question, since power is how you discuss energies over time. Part D, after the liquid reaches a constant temperature, so it's going to reach that constant temperature. Liquid reaches constant temperature. So what do we know is true at constant temperature? What we know at constant temperature is that the P in is equal to the P out. Very important to remember that. You can't solve this question without knowing that. The heater is switched off. So we switch off the heater, and so what's going to happen if we're no longer supplying heat? So if we turn this off, then all that's going to happen is power is going to be coming out. And so the substance is going to have to cool down. It's going to start to lose 35 joules of energy every second. It says the temperature of the liquid decreases at a rate of 3.1 Kelvin per minute. Use this information to estimate the specific heat capacity of the liquid. All right, so the very first thing I know that I'm going to need to do, and I might as well just do it now, is I know that the rate of change of temperature, so that's the rate of change of temperature, is going to be 3.1. Let me write that above the dots. It's going to be 3.1 Kelvin per minute. So what I'm going to do immediately is change that to seconds. And so I know that 1 minute is 60 seconds. And so that way I can get my minutes to go away and I'll have it in kelvins per second. And we know that that's going to be way more useful to us because the 35 watts is already in per seconds. And so we know we need to get out of per minutes and get into per seconds. The reason it was expressed in per minutes is you'll see why. Because if we do 3.1 divided by 60, which is what this unit conversion tells us, you get this crazy small number. And so the rate of change of temperature is 0.0517 Kelvin per second. So we have a very low number, and that's why it was easier to express this in per minutes, because 3.1 Kelvin per minute is a lot easier than saying 0.0517 Kelvin per second. Once again, we have a temperature change of a substance. It's asking us to find the specific heat capacity. When will I learn my lesson? It's asking us to find the specific heat capacity. We know that we need to use Q equals MC delta T, but not just any version of Q equals MC delta T, the one that has power. So PT equals MC delta T. We know what delta T over T is. We know what P is. We know what M is. We can find C. So the way to think about this is if I divide both sides by T, divide by T, then we can observe that we have delta T over T right there, which we know what that is because it's just this. So if I plug these numbers in, let's go ahead and do it. So we're going to get C. So the specific capacity is going to be equal to, all right, here we go. We're going to get power. So the power was 35 watts. Remember that the power in was equal to power out. So we were providing 35 watts, but then it was shut off. And because it was constant temperature, that 35 watts that was being provided is now what's being lost. So we're losing 35 watts. And that 35 watt loss in power, so 35 joules per second being lost. So now I've got my power right there. I'm trying to find the C, so I need to divide by the mass. I told us the mass was 0.24 kilograms. I'm just going to verify that because I might have forgotten it. 0.24 kilograms, nailed it. And then we're going to multiply by on the bottom, because we're going to divide this rate of change of temperature. We're going to divide that to the other side, which means we're going to need to put that on the bottom as well. 0.051, 0.0517 Kelvin per second. Okay, now because this is all like weird stuff, let's make sure the units come out to what they should be. So what should the units be? This is specific heat capacity. The unit should be joules per kilogram per Kelvin. So let's see if we end up getting that when we divide this. So we can see that the per seconds cancel out. And sure enough, there it is, joules per kilogram per Kelvin. So we know we're on the right track, and this answer should be correct based on the unit analysis. And you should always do this when you're solving physics problems. The units can guide you. The units can be your error correcting. They can make sure that you're doing it right. So 0.24 times 0.0517. And there's my answer, 2800. So the specific heat capacity is approximately 2800 joules per kilogram per Kelvin. So one more time, the way I know that is because the kilograms are on the bottom and the kelvins are on the bottom, so it's per kilogram per Kelvin. Okay, that's it. I hope this wasn't too long, guys. All I'm going to ask you to do now is to just submit a short reflection on Google Classroom, documenting what you learned by going over these solutions. If you have any further questions, please send me a private comment or email or hit me up on Discord. All right, I'll see you later, guys. Have a wonderful day. And I guess, hey, have a wonderful summer as well. All right, take care. Bye.